initially in the research sector with the CSIR, and then in the last 20 years have been in the consulting environment. And it's been a fascinating 30 years. Groundwater is never dull, always interesting. So I really enjoyed the career. And I'd like to provide a little bit of context for today's webinar, is that we're involved quite often in farmer meetings around licensing or with the public sector. We have some citizen science projects with WWF, and there's a wide range of understanding about groundwater, how it occurs and so on, to the point that there's a complete misunderstanding how groundwater occurs. And Christel just mentioned the one day after a meeting that we should really start some sort of a roadshow or something just around education of how groundwater occurs and so on. And then with COVID-19, we thought a little bit further about how we could do this, and then we slowly got to the point of, well, let's run a webinar around groundwater, and that's exactly how we are here this afternoon. So I must just emphasize, this is really around education about groundwater and just covering the basics. It's a vast topic, but we just want to cover the basics. It's not marketing, it's not a promotional afternoon or anything like that. It's purely educational. And the more we understand about groundwater, then the better it is going to be for the resource. You know, how does it link with springs? What is artesian flow? How does it contribute to base flow of rivers and so on? So the more we understand that, the better we can be at managing it in terms of a sustainable resource. I would like to move on to what I call the groundwater life cycle. We've just got a diagram that explains, and it's to structure this afternoon's talk, and don't be overwhelmed by it. But if we start with the kind of number one in the top right, Corné Engelbrecht is going to talk about the basic aquifer types. He will explain more about those and what an aquifer is and what is artesian flow and so on. And then moving on really to that first circle, number one, Neville Paxton is going to talk more about where do you choose to drill? Such a critical question. And then after that, you've drilled and hopefully you have a successful borehole. Kes Murray is going to talk further about how much water you can abstract sustainably from a borehole and how do you calculate that. He will also be talking about groundwater chemistry. He'll touch on that a bit. So thereafter, you've drilled, you've been successful, you know how much water you use. You must remember that all the water in South Africa, the custodian of that water is the Department of Water and Sanitation. And you need the authorization from them. So the legal aspects of water use, Christel van Staden will talk to that topic. And thereafter, you should all be good to go. And the crucial issue of monitoring, how do you monitor your resources and how do you manage your resources? That topic will be discussed by Dale Barrow. You'll see on the little circles going up to number 6 and number 7, there are additional groundwater techniques and skills that are used. We're not going to be discussing those this afternoon. So we're not going to be talking about, you know, numerical modeling, what happens in the vadose zone and the unsaturated zone, the geotechnical aspects, or the whole huge topic of contamination. And that we'll leave for another day. So great, thank you very much. Once again, welcome everybody. I hope those who are having sound problems can sort them out. But I want to move on with the technical presentations. And at this point, I'd like to hand over to Corné Engelbrecht to explain Groundwater 101. Thank you, Corné.
Good afternoon, everyone. My name is Corné Engelbrecht. I'm a hydrogeologist at GEOS. And I've been involved in all aspects related to groundwater from the beginning, from groundwater exploration all the way through to legal water use authorization and monitoring and management. Today, I'm going to give a quick introduction to groundwater, and I really hope throughout this webinar, it will be evident that there's a lot more to groundwater than just drilling a borehole, installing a pump, and trying to abstract the maximum out of that borehole. So let's first look at what is groundwater. Groundwater is water that is infiltrated into the ground to fill the spaces between sediments and cracks in rock. If we look at it in more scientific terms, groundwater is water found in the subsurface in the saturated zone below the water table. Then moving on, why is there groundwater? We all know and we all are familiar with the water cycle. If If we look at surface water is pulled downwards by gravity, either resulting in flow by means of streams and rivers, storage in dams, lakes, the ocean, or infiltration into the ground. Groundwater is mainly dependent on two factors, which is rainfall and also geology. And I'll be touching on that in just a second. Then the question, where does groundwater occur? We all are familiar with the term an aquifer. If we look at the terminology behind that, an aquifer is a body of porous rock or sediment saturated with groundwater. Groundwater will follow the path of least resistance, and groundwater flow and storage occur between unconsolidated sediments, solid rock particles, and between solid rock units. And that basically comes down to geology, to your specific site geology. And as I mentioned, the geology of the subsurface controls how groundwater will flow. As I mentioned a couple of seconds ago, so the two main driving forces behind the occurrence of groundwater is rainfall and geology. And that's for the simple fact that rainfall will introduce that recharge of water into your aquifer. So normally in an area where you have higher rainfall, you can expect to have either larger volumes of groundwater, higher yields, and also that has a positive effect on your groundwater quality. And then secondly, looking at geology, if you look at your specific host rock, at your specific location, some host rocks are known to be good hosts for groundwater and some are not. And we will be discussing that shortly as well. So coming to the explanation of aquifers and different aquifers. So there are two general types of aquifers. Firstly, a confined aquifer have a layer of impenetrable rock or clay above them, and then unconfined aquifers lie below a permeable layer of soil. There are many different types of sediments and rocks that can form aquifers. Aquifers are sometimes characterized according to the type of rock or sediments of which they are composed. And just to quickly summarize and list them, firstly is primary aquifers, also known as an intergranular or a sand aquifer. Then a secondary aquifer, which is known as a fractured rock aquifer. And then lastly, a karst, which is also known as a limestone or a dolomitic aquifer. If we go into a little bit more detail to explain these different types of aquifers, if we firstly look at a primary aquifer, or as I said, let's call it a sand or sandy aquifer, water moves through the intergranular spaces formed at the same time as the geological formation. It's an aquifer comprising of unconsolidated material deposited by water, typically occurring adjacent to rivers and in buried paleochannels. Alluvial aquifers are generally composed of clay, salt, sand, gravel, or similar unconsolidated material deposited by running water. And it's very important to note, sometimes they can range in thickness from 10 to 20 meters, or even up to 100 or 120 meters deep. And if you look at some local examples down in the Western Cape of primary aquifers, firstly, it's the Cape Flat Aquifer in the Philippi area, the Atlantis Aquifer in the Atlantis region, and then also very well known is the Sunveld area. If we move on then to secondary aquifers or fractured rock aquifers, that's where groundwater moved through secondary openings which developed after the rocks were formed. The secondary opening formed as a result of weathering, fracturing, faulting, and dissolution. And a fractured aquifer is defined as a formation that contains sufficient fissures, fractures, cracks, joints, and faults that yield economic quantities of water to boreholes and springs. So that's basically if you have water occurring in a hard rock formation, that is known as a fractured rock aquifer. And if we look at another example in the Western Cape area, Specifically, I want to mention the Table Mountain group, sandstones and quartzite, which is known to be a very good aquifer in terms of yielding good quantities of groundwater and also good quality of groundwater. Lastly, is karst aquifers or limestone or dolomitic aquifers. It's a special type of fractured rock aquifer in which the water in the fractures has dissolved the relatively soft rock, thereby significantly increasing the size of the fractures. The term karst is used to describe an area of limestone or other highly soluble rock in which the landforms are of dominantly solutional origin and in which the drainage is underground in solutionally in large fissures and conduits, or we can easily describe that as caves. And in the Western Cape, karst aquifers are not that greatly represented. One example that I just want to mention is in the Van Reinsdorp area, the Van Reinsdorp karst aquifer, especially next to the Trutu River. But up country, in the Gauteng area, they're quite well represented in that area, karst aquifers. And that's also, if you just think of sinkholes, then also karst aquifers come to mind. So after looking at a couple of principles in terms of groundwater and just a brief explanation of groundwater, the next thing is how is groundwater located? And for that, I will be handing over to my colleague, Neville Paxton, to further explain. He will be talking about groundwater exploration and drilling.
Thank you, Corné. My name is Neville Paxton. I'm based in the Eastern Cape branch in the beautiful town Groundwater, also a fine day outside. My professional speciality is groundwater supply all the way up to impact assessments. We know as we change an environment, it impacts the environment and it can even impact your groundwater. But today I'm going to focus on how we find groundwater. And if you give me a second to share my screen, I'm going to answer that ever important question, waar moet ek boor? When we think of groundwater, when you're having a nice chat with mates at the bar, we talk about groundwater in a very loose manner. We see a lot of photos such as these on social media these days. We see, as on the right here, a massive gushing column of water coming out of a borehole. We see water flowing out of artesian well, what we call water that flows at the top of the casing, and we think, wow, this is the kind of thing that we really want, because you don't need power, you don't need a pump, you just need to dig a channel to your closest dam. It really gets you excited, and these are the things that entice us to drill holes, to spend lots of money. These are also the things that drillers tend to use to advertise their business. Some of the terminology or statements that you often hear when discussing groundwater, you'll hear somebody like Dr. X found new groundwater. People talk about veins or aura that often cross in your driveway. We often hear in our profession that boreholes are suddenly dry. Because it's my borehole, it's my groundwater, I'm allowed to use as much as I want or use it until it's finished. And then, as Corné touched on, people also talk about underground dams, your karst aquifers, a huge topic, especially here in the crew, is divining. And people who show you where to drill often brag about success rates of 90 to 100%. And at the end of these conversations, I want you to think, but what does groundwater really look like? We need to know more about it before we start throwing money at developing it. So here's a much more boring picture. This is on a road cutting between Groundwater and Murraysburg. And this is you're actually looking at what groundwater looks like on the surface. This was taken during January of this year, where we had phenomenal rains over about a 2 or 3 day period. And a week later, the surface water had already evaporated. Our dam was still empty. The rivers had stopped flowing. But you still find this very dark zone in this road cutting a week later, and that's essentially a saturated zone in those fractures. So this is a fractured aquifer, and this is some of the benefit of groundwater development. Long after your surface water has gone, you still have groundwater in your fractures. We call that a lag time. Here I've got a short video to show you what groundwater looks like when you actually put a camera down a hole. So at GEOS we've got a borehole camera, and it has the ability to look straight down into the Earth's core, and we use it for many various applications. The top left of this picture, you can see that our depth of the camera is actually 59 meters below the surface, and we've also got a date and a time there. So if I press play, you'll notice that there's particles floating around. Bearing in mind we are under the water table already, so we're in that aquifer and we're moving down looking towards the Earth's core. Then this camera has the ability to switch to side view, and we can see all this white mineralization on the borehole side. I'm going to stop the video here because I want you to note at the depth of 60 meters, we've got a fracture which is probably 2 or 3 thumbs thick. And you can imagine what kind of hydrostatic pressure is necessary to keep a fracture open at a depth like that with a massive tonnage of earth above it. So if I press play again, we'll also note at the bottom right of this video, we've got a little creature moving. And that's what we refer to in science as a steigerbite, a groundwater crustacean, of a Groundwater kreef, and there's actually 2 of them. The one has something in its mouth, it's got food, and the other one wants to fight it off. So this is phenomenal footage. Now the take-home message of this video is not the steigerbites or groundwater crustaceans, but it's the fact that for these to survive, they've got to be able to travel vast areas. They've got to be able to feed and to mate, and to do so, they need big fractures. And that's the point of the slide. We're not targeting a thin vein or an R. We are looking at a big fracture network where these steigerbites can survive. And this is not common. It's not in every borehole, but this just shows you the magnitude of what we need to spend our money on to develop. I'm going to stop that there. Here's another picture of what groundwater should look like. Now this is a municipal supply borehole for Lambert's Bay. Also no fireworks here, but this is a borehole that's got monitoring equipped so that they know exactly what the water level is doing. It's got a flow meter equipped so they know how that level is reacting to the volume that they abstract. And this is the lifeblood of Lambert's Bay. There's another borehole similar to this, and it's a secure, well-managed resource. So if we go back to that slide of the statements we often discuss when having a beer, when somebody says, I found new groundwater, bear in mind that it has already been there. We know from Corné's talk that it originates from rain. Often the quality is an indication of how old the water is. If it's quite saline, it could be older water. If it's fresh, it could be freshly recharged from recent rainfall. If somebody talks about veins or aura, we've already looked down a borehole. We've looked at a road cutting where we can see groundwater. And we know now that it's a 4-dimensional anomaly. And by 4-dimensional, I mean it can be orientated in various ways. It's not a hit and miss kind of question. And also there's a temporal factor to it. So in times of high rainfall, your water table might be higher, and in times of drought, it might drop. When somebody says to us that their borehole is dry, it's very important to establish in what context that story comes about. Obviously, originally, it was worthwhile putting a pump down, so it went from being a production borehole to dry. Is it an environmental factor? Did somebody drill very close by to you? Or is your pump just too big? And that's often the case. The fact that people think that groundwater is inexhaustible or it's their resource is unfortunately not true. It can be depleted. There's also connected. If you share geologies and you're close by, often boreholes are connected to each other. There's ways to determine that. And when somebody looks you in the eyes and tells you that you've got an underground dam under your borehole, drill right here, be wary, because that's rock specific. We know that it occurs in Van Reinsdorp and in Centurion. As Corné mentioned, we've got sinkholes, and that occurs when people take all of that water out of an underground dam. And because there's no more water to keep that cavity open, we have sinkage. So you're not going to find that in a place like the Karoo, for example. Divining, very big topic. It's not a science. It's not proven. In fact, it is proven to be only as successful as chance. I'm not going to talk too much on this because I'm not a diviner. There's just an excerpt there from a Major General of World War II that said in bold there, the water diviner's assistance has been absolutely worthless. They had to use diviners at that time. We've got different options these days. If, for example, you do like divining or believe in it, that's fine. At the bottom right there, there's a way that you can make your own divining rod. So here's the big question. Contrary to what a lot of people will tell you when they come to site a borehole, no one can actually see under the ground. So how do we know where to drill? It's actually a question of minimizing the degree of uncertainty. So how do you do that? Well, firstly, you can appoint a professional. And the hydrogeologist will start by doing a complete investigation of your property, be it a farm or in the industrial area or even your house in town. And that investigation comprises of 3 main steps. The first one is a desktop study. So we'll sit in the office and we'll look at satellite imagery, which is freely available on Google Earth. And I want to emphasize here that I think every landowner should have Google Earth. It's an extremely powerful and free tool. You can pretty much do any measurements with it. And then what a hydrogeologist does, he couples that with geological maps, and then you get a good idea of what's going on in your property even before coming to site. The next step for hydrogeologists to do would be to come to your property and conduct a hydrocensus. And what that basically means, he's going to visit all your friendly neighbors and gather on their boreholes, and that usually involves borehole depth, borehole yield, borehole quality. And just from step 1 and 2 already, we know that if you drill on, for example, a shale, similar to what your neighbor has, you can get similar results. You'll probably have an average yielding borehole with poor quality. Then you know if that poor quality is not good enough for my use, I want to use it in my house for drinking, I'm probably going to have to treat it. So even before drilling, you know what to expect. And the third step is to actually visit the site. And this is critical. We find more and more often that clients or people are getting recommendations on where to drill without the person even coming to your site. What should happen is they come to the site and they look at the areas that interest them, the geologies that stand out, they do the hydrocensus, and they often actually tweak it or redefine it to be more certain of where to drill. And after that, if there's very little to see on site, they might use geophysics. And this is just one method that we use to decrease that degree of uncertainty and to ensure a successful result. So at the end of these 3 steps, you're going to get a conclusion that says drill here, here, and here, or even don't drill. And don't drill is just as important, because if your geologies are poor and your qualities aren't what you need, you might have to look at alternatives like rainwater harvesting or water reuse. At least you've saved the money of drilling and the requirements thereafter. So now just briefly some more on geophysics. So as I mentioned, this is only one tool of many that we have to find the target rock or aquifer, that rock that has the best chance of holding water. Certain geophysical methods are better for certain rock types than others. And to discuss that, we've got 3 main geophysical methods in groundwater exploration that have a long history and a proven success rate. And it's actually be defended scientifically. And these are the magnetometer, the resistivity method, and the electromagnetic method. Each one is specifically suitable for a certain kind of rock. For example, the magnetometer is based in the Karoo, where we've got dolerite rocks, which give off a magnetic anomaly. The disadvantage is I can't use this in a built-up area because buildings have metal in. Then we've got the resistivity method, which is really good for finding fracture zones in your sandstones or your Table Mountain group. That's the rock that Corné discussed, which has recently become quite famous internationally because it's notorious for, not notorious, it's well known for high yields and good quality. So the resistivity method will show us where that rock is most weathered. The disadvantage of the res method is that you've got to hammer pegs in, and if you've got shallow rock, it's quite tricky hammering those pegs through hard rock. Then we've got the electromagnetic method, which is good for all rock types, especially when you've got contact. So you've got, for example, a rock where water flows quite easily, and then you've got a rock where water doesn't flow very easily. Where those two have contact, you can have groundwater changing. So it'll flow from the easy flowing rock against that impermeable rock, and it'll slow down in flow, and that's something that we target when looking for groundwater. But the important thing here is that each method and tool has a specific application. It can work only on a certain rock type or family, and if that data isn't understood or interpreted correctly, it'll be wrong anyway. So when somebody comes to your farm or your site with one of these and he uses it for the wrong rock, or he comes with something that looks like a gun, just be wary, ask him how it works, make sure that it's applicable and it can work between buildings like they claim, make sure it's logical and practical. So if we briefly look at some examples, I'm going to show you the resistivity method and how it works. As a site, just basically on your western side or your left side, we've got this developed land. On the right side, the grey motley pattern, that's really rugged terrain, difficult for vehicles to access. And in the middle there, we've got the manager's house borehole. So the hydro census has been done. This is all they have. And the farmer needs more water. So just from a satellite image, very little to look at, a difficult site. Go to the site, look around. We find that we need to use geophysics, and we do. Luckily, we've got access to geological maps, and I've just overlaid one where they still used to draw the geology by hand. And all you need to know here is that the Table Mountain group, that famous aquifer, is the one in the blue, and then we've got this striped pink line going right through. That's what we call an inferred fault. And it's striped because the geologist who drew this wasn't sure where the fault is. So fault is a target for groundwater development because that's where displacement has occurred and lots of fracturing. So that's your path of least resistance. That's where you're going to find water. So what we did was we did a resistivity profile along the black line, trying to get as perpendicular over that fault as possible. And this was the result. So the resistivity profile, which you see here, both on the black line and in the bottom left corner, you just have to understand that the scale works as follows. Your blue is your soft material, and as it moves through to green, yellow, orange, and red, and finally to purple, the rock becomes harder and harder. So if we plot the fault, we can plot it according to this profile. You can see that almost the whole left section of this profile is soft material, and then suddenly you have this very hard rock. So the fault is actually 200 meters south of where it was originally mapped. Then we can plot the hydro census borehole on the resistivity profile. We can see that they drilled into that hard rock. That's probably why it's low yielding. So what we did is we decided to site the borehole in that faulted zone, but we moved it all the way to the east as far as possible so that we can avoid impacting area that needs to be cultivated, and so that we can avoid artesian conditions. When you drill into an area where there's lots of layers that are impermeable above your aquifer, the recharge is higher up than your borehole, you often get confined conditions and water flowing uncontrollably out the top. And we want to avoid that. And what this resulted in was a borehole that yields 25 liters per second or 90,000 liters per hour. And this has been tested and it sustainably delivers this 24/7. Okay, so now we're going to look at the magnetometer. Remember, I said that this method is best for your Karoo, and in the Karoo we've got a lot of lineaments, or the straight lines or ridges. It's also referred to as Eysterklip, Eysterbank. And in this slide, I've just highlighted them with red lines. We've done that hydrocensus, and the farmer here needs more water to develop his lands. The existing bores are low yielding, so we went in and we did the magnetic method across these dikes. So the yellow line in this case is the path where I did the profile or the traverse. This graph gives the result. All you need to see here is this blue line, which is pretty flat for the first 100 meters, and then all of a sudden there's a serious spike and another spike. Those correlate very well with where these two dikes are. It's actually a double dike. And if we plot the position of the existing borehole, wind pump 2, we see that it's on the down gradient side of this dike. So what we did is we plotted a new borehole on the up gradient side of the dike, and that resulted in a borehole which gave a blow yield or an airlift yield of 30,000 liters per hour versus the 200 liters per hour. And it was not because the first person sighted incorrectly. He sighted on the right structure. However, geophysics allowed us to see how this dolerite dike dips. And you want to sight on the up gradient side of the dike because the center of that dike is impermeable. So it essentially acts like a dam wall. If you sight on the down gradient side of the dike, you're going to have far less water to no water than on the up gradient side of the dike. So this is basically what happened in that study. We've got that wind pump wall on the down gradient side of the dike. You can see on the up gradient side of the dike where all your surface water flow is, your rainfall channeling into rivers and actually feeding this fractured zone around the dike. We then drilled a new borehole and intersected at good depth to get those good yields. So now that we understand where to drill, we have to go ahead and drill. This is not a simple process. It's not like drilling a hole to hang your mother-in-law's portrait on. It's got to be a straight hole, obviously. It mustn't be hidden away. It must be a safe hole, and it must be usable. You want an end product that's usable. So you've got to start this process by getting a reputable driller, someone who has experience in the area. He's got references. He hasn't just started up his business. Drilling's not an easy job. And you can ask him various questions. The main or the most important one is probably, do they understand what borehole development means, which is boorgatontwikkeling. And basically what that means is they flush that borehole out with that compressed air until that water becomes clear or as clear as possible. And that's extremely important, and it's often overlooked. Often at the end of the hole, they'll pull out their rods and go home. But after drilling development, after flushing out a hole for a certain period of time, you remove sediment from that borehole, and that does two things. It ensures that when you put your pump down, your pump doesn't suck up the sediment and get damaged. And it also promotes the cleaning up of those fractures. So all the sediment is removed out of those fractures, and that promotes the capacity of those fractures to deliver water into your borehole. So extremely important. If the driller doesn't know what boorgang means, save your airtime, put the phone down, phone another one. Then we've got to have a drill certificate on completion of the borehole. It's a simple document. If it's not handed over to you, essentially the bore is not complete. If you, for example, were wanting to buy a house and the seller tells you that the electrician said that the wiring is shop, you can be concerned. You want a wireman certificate. It's the same principle here. Once that bore is complete, the driller must give you a document that tells you what the borehole depth is, the water strikes, which is where they found the water, what that blow yield is, and a basic description of the bore chips that come out. And it doesn't have to be a geological description. It can be literally black to red to grey rock. And concerns, the driller will know if there's a concern for collapse. If the water had a funny smell, he must note that, obviously at the date, and then the location and the name of the bore. It often happens that you drill 2 or 3 or 4 boreholes in one go, and if you confuse those names, you can end up putting your pump down the wrong hole, which is an extremely expensive and unnecessary exercise. And then your driller has to be capable for the relevant formation. In South Africa, we've got different geologies. We've got a lot of different professors coming to this country to study here because we've got this wide variety of geologies. That means that your driller has to be capable for those different geologies. For example, you are on the west coast in that unconfined aquifer that Corné talked about, you've got to use the mud rotary method. That's specific for loose sands and clay. And in this method, as the driller goes down, he uses a fluid to keep that loose stuff from collapsing into your borehole. Then we've got a lot of rock in South Africa. So the most common method is the air percussion method. And that we often see where you've got a drill rig and another rig having a huge compressor on, and they just drill away. It makes a lot of noise. It's very effective, cost effective and time effective. And then on the other hand, you've got the ODEX method, which can be done before air percussion. And this is specifically needed when we've got problem formations like lots of clay, which suck onto your drill bit, or loose rocks or pebbles in an alluvial area that can bounce around. And if, for example, they do normal air percussion in an area like this, you can end up getting casing tearing, or the driller can take 3 or 4 more days on site, which you don't really want. It becomes a real mess. And then your borehole design. The design of that hole has got to be specific for your need. For example, if you're going to put up a large-scale irrigation borehole, the diameter has to be far bigger at the start and then telescope down. Very different to what I'd use in my garden. For example, I'm going to go for a cheap, small diameter hole because I only want to irrigate every second day. Then I've got to think of potential collapse. If that, whilst I'm developing that hole, for example, and the water stays turbid, there's large fractures, as you can see in the top right corner here, almost as big as my hand, then I know that there's a good chance that there's continual eroding in that hole, especially if there's high volumes. And that means that it's absolutely worth it to spend extra and line the whole in of your bore with a PVC lining. If my water is aggressive, it's got a low pH, often in the Western Cape, it's below 7, it can be 4. Then you've got to question, how long is your steel casing going to last? Should I go for better quality steel, or should I go for PVC from the start, which will definitely last longer in the acidic water? Then in the bottom right picture here, you can see the guys cleaning up a site. This is in a river bend almost, or a paleo channel where water used to flow. And here we need to make that borehole as visible as possible, so you can find it easily, obviously. Also, should that flood come, that 1 in a 100-year flood, you've still got the casing above the surface, and you've got no potential contamination occurring from flood water going into your hole. Because we've got lots of human activity in this area, it's a potential municipal hole. We need to seal that hole with a cap and even spot weld it until it comes into use. If, for example, your friendly neighbor decides to throw a rock down a hole like this, it's an extremely expensive case. You have to go re-drill it open, something you can avoid by doing a simple exercise as such. So now that you understand more about what groundwater looks like, you need to bear in mind that drilling is actually only the start of sustainable groundwater use. Whenever you decide to show you where to drill, make sure that the reasoning behind that position is a logical way. Ask them, why did they drill below the dam wall? We all know dam walls leak. Ask them certain questions that they should be able to answer you in a clear report so that you can revert back to it at a later stage. Drilling is not a process that you should repeat every year when the budget becomes available. It's not a hit and miss story. It's actually a once-off project where you might have to drill more than 1 or 2 boreholes, and thereafter you have to spend your budget in testing and monitoring that hole. If you have more questions, I'll be at the end of this slide. I'll be willing to hear them, but I'm going to hand over now to Kes Murray, who's going to tell you more about the very important next step of testing that borehole. Thank you very much.
Thank you, Neville, and hello to everyone. My name is Kes Murray. I'm the Yield and Quality Testing Business Unit Leader at GEOS South Africa, and I've been working there for a number of years. And today I'm going to talk a little bit about what is involved with accurately yield testing a borehole, as well as how the borehole should be sampled so that we can get some good quality results and understand what that groundwater quality really is. So I'm going to start my presentation now. Here we go. With what are the South African national standards for the yield testing? So we do have national standards on this, and the main focus of the difference between these standards and other forms of testing that we have in South Africa is the methodology in the type of testing, and that is that we use a constant discharge test as opposed to a test where we have potentially a constant head and we monitor a changing flow rate. In the national standards, we are required to do testing that has a constant flow rate for the duration of the test. And from that, we can then analyze that data to produce the following results. So we look at the sustainable yield of the borehole, and that is what we define with the sustainable yield of the borehole is how can we pump the borehole in a way that we won't cause so much drawdown in the borehole that there's a negative impact to something. And that can be to the pump itself. If the water level draws to the pump and causes the pump to burn out, it can be to water strikes that have been intersected in the drilling of the borehole to make sure that we don't dewater those. It can be something like not drawing the water level to a sufficient point that it will impact on a neighboring borehole, anything like that. We define a point that we don't want to draw the water level below that point and work out how we can abstract the borehole in a way that we won't exceed that drawdown point. We can also then look at how should the borehole be correctly equipped. So it's not enough to say, okay, the drilling's finished, we'll just throw in a pump that's approximately the same as the airlift yield. This is quite an issue in South Africa of the driller finishes drilling the borehole, they do the airlift development of the borehole, and they say, when we're doing the airlift development, we had 10 liters per second flowing out of the borehole, or we had 60,000 liters per hour. And then the client then goes and purchases a pump that goes in the borehole that is suited to that yield, which might be completely wrong compared to the sustainable yield of the borehole. And that results in the borehole ending up dry after maybe a week or a few months, or maybe it takes a year, but quite often it's shorter than that. So we also then can look at what a pumping schedule should be. Some boreholes can run, in fact, most boreholes, if you have the correct rate, can run for very long periods of time sustainably. So continuously 24 hours a day for years on end if we get the rate right. In some boreholes, there are boundaries in the aquifer that require us to have some recovery time for the pumping of the borehole. And then we can look at something where if we have a solar powered pump, we can have an 8-hour pumping schedule with a 16-hour recovery period each day. Or we can have sometimes seasonal irrigation where we have 6 to 9 months of the year we are abstracting groundwater to irrigate, and then we have a recovery time of 3 to 6 months a year for the whole aquifer to recover from that. And then lastly, we can look at what is the influence between this borehole and other boreholes in the area. And that is quite important in cases where we have a municipal supply borehole that might be near to an agricultural supply borehole, to make sure that those two are either abstracting from different resources, or if they're in the same resource, to ensure that that shared resource is used responsibly and sustainably together and not one drying out the other one. Okay, so these are the national standard guidelines. And one of the important parts is I've spoken about the type of test, in that we need to have a constant flow rate for the duration of the test. So that is incredibly important. What we do is we pump it at a fixed rate and monitor the drawdown in the boreholes, which is the change in water level from where the water level started, or the rest water level when there wasn't pumping happening. So that's very important. The second important part is the duration of that constant discharge test. So you can have a borehole that is maybe supplying 1 or 2 liters per second, and it's 1 out of 10 boreholes that are on a farm or that supply a municipality. That is not a high risk borehole in terms of being a critical supply. So if something goes wrong with that borehole, which it shouldn't, but if it does, there isn't this whole water scheme that is based on that single borehole. So there we might want to do a 48-hour test if it's for a town supply, or maybe if it's for irrigation, we can even do a 24-hour constant discharge test. If it's a single borehole that is supplying the whole area, or if it's a case where we have 1 or 2 boreholes, but we have no surface water to buffer our water use or our water requirements, then we might look at saying, okay, we need to do a 3-day test or 72 hours, and potentially even longer, sometimes a 5-day test, or even longer in the case of some municipal supply boreholes. So how this test actually happens is in 3 parts. We have a step test, which happens right at the beginning, and this is to get an idea of what rate we should run the longer form constant discharge test at. And so we pump the borehole at a couple of different rates, usually 4, but sometimes 5 or 6, to see initially how is the water level dropping when we have a constant rate pumping, but just for a short period of time. And that step test, the purpose of that, you can use it for some analytical flow equations and stuff like that. But most of the time, what we're looking for with that step test is to recommend a suitable rate that we can do our constant discharge test at. So there's no point in having a borehole that's 150 meters deep. We've got a pump that's hanging at 120 meters in the borehole, and we do a 3-day test, and the water level drops from a starting water level of 10 meters and only drops to 15 meters over 3 days. That's not going to tell us in the long term how is this borehole going to respond when the whole area's water level drops to maybe 50 meters or 60 meters. We need to really pump this borehole in the test in a way that we drop the water level significantly far down in its available drawdown of where it starts with its rest water level to ideally its main water strike. And if we don't know that, then to where as deep as we can get the pump, or down closer towards the end of the hole. So if we have a shallow borehole, it's not too much of an issue if we're a couple of meters out. But if we have a 200-meter borehole, or even a 100-meter borehole, and we're only getting 5 meters of drawdown or 6 meters of drawdown out of an available drawdown of maybe 80 meters or 90 meters, then we haven't really tested what the borehole's capabilities are. So that's the constant discharge test. At the end of that, then we monitor the recovery of the water level or the drawdown back up to its starting water level. And this is very important to do correctly, because this, first of all, it confirms some of the calculations in the constant discharge test that we make on the constant discharge test. But more importantly, when we look at the recovery, we know under ideal conditions where we expect the water level to recover to within a given amount of time. So if it's recovering faster, it's giving us an indication of there might be an aquifer that's leaking into the aquifer that we're accessing and supplying more water than we expect to be supplied from this borehole. Or it might be an indication if the recovery doesn't match up to where we expect it to be at the end of the recovery period after the testing, it might be an indication that we're dewatering the aquifer. And this can be a serious problem. Sometimes we have very high yielding boreholes that have yields of maybe 20 liters a second or even higher, and we do a constant discharge test and the water level drops very slowly during that test. We monitor it all accurately. The test lasts for 3 days. We switch the test pump off, and then the water level recovers maybe 30% and then just stops at 30% recovery for the next 3 days. Then we know we're dealing with an issue where the water can flow well through the aquifer, but the aquifer isn't extensive and it isn't connected to larger fracture networks, if it's a fractured aquifer, or if it's a porous aquifer, that it must be pinching out somewhere, and we're actually dewatering that, not dewatering that aquifer, but we are removing storage from that aquifer. And that can have a serious implication to how we use the groundwater from that borehole. So here's a couple of examples that I've pulled up. Now, a quick thing on this. This is a constant discharge test examples, and these are plotted on a semi-log plot. And I'll explain briefly why we do that on the next slide. But for now, just note that the y-axis or the vertical axis is linear, so it's going in multiple units up, 0, 5, 10, 15, etc., or 0, 10, 20, and the x-axis is logarithmic, so it's going 1, 10, 100, 1,000, and that can, in this case, it's minutes for the test pumping, but that can be days as well if we're doing very long-form test pumping, or hours if we're doing it that way. And from these examples, what I'd like to highlight is the information that we get from these type of tests. So we can see where the drawdown curves change angle. Those are indicating boundary points in the aquifer to us. It's also important, so we can see that quite clearly in the top two examples. We can see these inflection points where the water level is drawing down at a certain gradient, and then it inflects and begins drawing down faster. And that can help us realize that there is potentially a boundary within the aquifer. And a boundary in the aquifer can be something like what Neville was talking about in the previous presentation with a dike, that is a physical barrier inside of the aquifer that is blocking flow. For instance, if we're in a sandstone aquifer, or for some reason we're in a high-yielding shale aquifer, maybe there's a large fault zone or something like that going through. But if this is then crossed by a dike, and we have a physical barrier over there, in the early time, the groundwater response to the pumping is as we expect. And then with these inflection points, we start seeing the flow to that borehole gets impacted on by the boundary. So that's very important to take into account. We can also look at these in terms of what are characteristic curves. So in the bottom left-hand side, we have an unconfined aquifer characteristic response. And this is very important to know about the aquifer and the borehole that's in it, because if we have potential sources of contamination and we have an unconfined aquifer, the borehole will be much more susceptible to those sources of contamination. So if we have a filling station or waste site or something like that in the area, and we have an unconfined aquifer with a production borehole, we're going to have any rainfall that can pick up potential contaminants and infiltrate down into the aquifer. Those will easily be accessed by the production borehole. And whereas in a confined aquifer, we would have a clay layer or maybe a thick shale layer or something like that that prevents surface contaminants from infiltrating down into the aquifer and impacting whoever is drinking or using that groundwater. Finally, on the bottom right-hand side, I've put an example of a recharge boundary. This is usually more frequently looked at with derivative plots. But a recharge boundary is also very important to know about a borehole. And in this case, it's a borehole that's into a fractured rock aquifer, but there is a nearby surface water source. In this case, it's a dam, and the dam leaks straight into the fractured rock aquifer. So when we do the pumping test and we start pumping the water, and we confirm this later with chemical studies of samples of the water in the dam, we start abstracting water from the groundwater. And as soon as there's a pressure gradient to draw water back towards that borehole, the dam starts leaking into the groundwater over there. And so this means, in essence, if we use this borehole and pump it to the dam and use the dam to supply irrigation or a town or something like that, in essence, all we're doing is just recycling the water around and around between the dam and the borehole, which is not very effective at all. So that's another interesting thing to know. This can also play a huge role in cases where we have surface water bodies such as a river. Even a dry river can still have base flow beneath the river, and impacting on that can be an issue when it comes to licensing the groundwater abstraction. So finally, there's an example on the right here that shows what Neville was talking about earlier. If someone says, you know, they found new groundwater, this was a test pump that we did. Only one of those boreholes on this graph. This is now a linear graph, so it's not on a semi-log plot. only one of those boreholes was being pumped for the test pumping session. The other 5 boreholes, or the other 4 boreholes that are on the graph, are all monitoring boreholes. And we can see one right at the top of there didn't respond to the test pumping at all. But in fact, the other 3 boreholes all responded quite clearly to the test pumping. And in this case, we know if we use this borehole for production, it's going to impact this, abstract this borehole, dry up those monitoring boreholes. So a brief history on the groundwater flow equations. We have about 85 years ago now, Tice came up with an equation for confined aquifers. I'm not going to go into much detail on this, but a lot of the flow equations following on from that are all based back on his original analytical solution for pumping a borehole in a confined aquifer. There was an approximation of that by Cooper and Jacob. Newman defined an unconfined analytical solution for test pumping of boreholes. Barker did the same for a fractured rock aquifer. And then in South Africa, we have the FC method, which was based on the work of Gerrit van Tonder, and that looks at the derivatives of the drawdown curve during the test pumping. And essentially the idea is what I explained right at the beginning with the sustainability. We define a point at which we don't want to drop the water level during production. And from the test pumping, we define an analytical solution that fits that curve of data. And then we extrapolate that to a reasonable period of time for use of the borehole. So this could be a couple of years. It could even be a couple of decades if we want to take into account drought cycles and stuff like that. And we see how far down that water level or that drawdown would be extrapolated. And then we make a recommendation on how to use the borehole based on the relationship between the rate that we do the test at and how far that water level will be extrapolated down. So that's a quick basic summary on what the analytical side of it is for the sustainable yield of the borehole. Okay, so now we've done the test pumping, we've analyzed the results, and now we put together what are the recommendations on the way to go forwards with this borehole. Well, first up, we have the location of the borehole, the depth of the borehole, and the diameter of the borehole. Very, very important information for when we look at actually equipping this borehole for production. We want to make sure that the pump isn't too big. Neville spoke about that earlier. There's obviously high risks in terms of putting a pump that's too big in terms of dropping the water level too far. Another risk is that you might purchase a pump just based on the yield and it might not actually fit inside of the borehole because the borehole was drilled too narrowly. This can be a thing of, in this case, we have a 165 millimeter diameter borehole. We wouldn't want to put a pump in that is maybe 160 millimeters because that only leaves 5 millimeter space inside the hole, and that's about 2.5 millimeters on both sides. So what's going to happen is there isn't enough flow of water around the pump to cool it, and we're probably going to burn the pump out quite quickly. Then we can look at the actual use of the borehole. So what rate should we be pumping it at, and what pumping schedule should we have? Is it a borehole that needs recovery daily? Is it a case where we're going to equip the boreholes with solar-powered pumps, in which case we're only going to be pumping from 8 to 10 hours per day? Can we adjust the recommendations to meet that pumping schedule? Is it a case where it's going to be on 24 hours a day indefinitely as a municipal supply borehole? Or is it going to be a seasonal irrigation where we're looking at 9 months of the year in some cases, or 6 months of the year in other cases, and we know we're going to have the seasonal period of recovery when the rains come? Finally, and most importantly, is where do we install the pump and what specific characteristics of the borehole do we need to take into account when choosing the pump type? So the pump depth is an important one to get correct because we don't want to have the pump too deep, such as right at the bottom of the borehole, and then there's a sump of sediment that ends up filling up and surrounding the pump and clogging it. We also don't want it in a case where we have the potential, if the borehole isn't well managed, that we can dry up the fractures or the saturated zones in sands and clays that are supplying water to the borehole. So we don't want to put it below those. Ideally, we want to put it in the middle of saturated sand layers so that the water flows laterally and laminar to the borehole pump, but it can be above them as well. It's important to have a critical water level that has we can put a cutoff switch over here to make sure that the pump doesn't, if the borehole is left on for some reason that is above what its pump schedule is, or for some reason it's pumping at too high a rate, or perhaps a new borehole gets drilled nearby and starts getting used and the water levels drop more than expected because the two boreholes are interacting. We don't want the water levels to just drop to the pump inlet and then the pump motor burns out and we now have to replace the pump. So we have a critical water level over there, and this can be something that is just above the pump to protect the pump burning out, as I just explained, or it can be a case of if we have multiple water strikes and we want the borehole at one of the deeper water, or the borehole pump at one of the deeper water strikes, but we want to ensure that we don't drop below a certain water strike in the next few years, we can install a critical water level cutoff switch at that level to protect that specific water strike. And then most importantly, the expected dynamic water level. So this is a prediction that we come up with from the test pumping data. And this is important because let's say we have a borehole that is 150 meters deep and we're planning to install the pump at 80 meters because that's the optimum point to install the pump for that borehole. If we then have a pump that can produce the 4.5 liters per second that we are saying is sustainable from this borehole, but the pump is suited to only lifting water from a depth of about 15 to 20 meters, and we actually need to lift it from maybe 60 meters, then the pump isn't going to work well for producing that 4.5 liters per second when it is switched on. The alternative, or the opposite of that, can also be the case where the pump is over-spec'd, not on rate, but on the lift that it is designed for, and then we can end up over-pumping the borehole anyway. Okay, so if we have monitoring boreholes, and this is an either-or situation, if we have monitoring boreholes for the test pump, for the pump testing period that we have monitoring data from them where they were observed for the test, we can get quite good aquifer characteristics. And from that, we can use groundwater flow equations to look at whether we expect to impact other surrounding boreholes or not. And this can be very important in the case of a farm that has a borehole that's near the boundary of the farm and the neighboring farm decides to put a borehole on their farm that's close to that one. That can be a potential source of conflict between the two groundwater users. It can be the same for a municipal supply borehole that is newly put up near an industrial borehole that's supplying factories with water, or it can be a municipal supply borehole where a mine has come up and put a new dewatering borehole nearby and might impact on the municipal use. There's a whole host of scenarios where impact between different boreholes can become a serious source of conflict in the future. But as sort of the theme of this whole presentation and discussion is, groundwater is not this magical thing. We can collect data on it, we can measure it, we can monitor it, we can manage it. And collecting data with test pumping specifically, we can start looking at whether we expect those interactions to happen, and we can adjust our recommendations accordingly to protect the interests of the other groundwater users in the area. So at the end of the test pumping period, at the end of the constant discharge test, we often take a groundwater sample at that point. And the point of taking the sample then is that the borehole has been well flushed and cleared of anything that was left over from the drilling. And now the groundwater that is coming out of the pump is representative of the aquifer that is surrounding it. And this is important to sample and to get analyzed for chemistry so that we can see what is the groundwater suitable for. Is it a very acidic water with a low pH? Is there a high salt content in the water that the salinity won't be suitable for the crops that are going to be irrigated with it, or in the factory that needs to use it for producing a product or cleaning? We can also take a look at some of the metals that are in the water. Some of these can be carcinogenic metals, and that can be a serious problem if we're supplying it to a community or for a town supply. And then we can also look at the microbiological contents in the water. And again, this is according to the South African national standards of what is required if we want to license a borehole. We need to understand the quality of the groundwater according to these parameters and these limits. So on the right-hand side of this diagram, you can see we have limits for most of these parameters, and those are either according to aesthetic values. So if the water doesn't taste nice and isn't pleasing either in smell or in taste, there's some limits for what those parameters should be in the water. And then it goes all the way up to chronic health where if we supply water that has, for instance, cadmium or uranium or cyanide in it above a certain limit, and for an extended period of time, we can start causing some serious health issues to the people that are drinking that water. Another concern with the metals in the water is quite often the groundwater is in a state where it doesn't have a lot of oxygen in the water, and so the metals are completely dissolved. And once we bring that water to surface, we oxygenate it, or even inside the borehole, just from the pumping process, we can oxygenate the water, and that can cause these metals to precipitate. And quite often that, coupled with microbiological contents that will feed on these precipitated metals, can cause clogging in the borehole and the pumps, and I'll talk a bit more about that in a second. So these are a couple of the more standard chemical diagrams that we produce from these samples, and these can be used to compare different groundwater chemistries to each other to see whether they are a related groundwater resource. At the top we have, on the right hand side, we have the Piper diagram, and below that the stiff diagram. The Piper diagram is relative concentrations of the salt ions in the water, and so this can be used to look at waters that are fresher waters versus waters that are from perhaps a saline type aquifer, such as a shale aquifer. We expect to have the shape that we have in the stiff diagram below, as well as where the 3 points are plotted in the Piper diagram over here, because a lot of our shale deposits in South Africa were under marine conditions, so we have a lot of sodium and chloride in the rocks, and then that leaches into the groundwater. The diagram on the left-hand side is a sodium absorption ratio diagram, and this is about the salinity hazard. Specifically for irrigation and crop types, there's a little bit of variation, but what it's looking at is the salt content of the water, and specifically the sodium content of the water, a hazard to a specific crop type. And if it is, that needs to be addressed before we just irrigate with that water and have a very low yielding crop just because of the quality of the water. Finally, we can get quite a lot of information from a borehole where we have a lack of information by putting a camera down the borehole and taking a video and taking pictures of the inside of the borehole. So there's quite a lot of things that we can do this for. One of it is to inspect that the drilling was done correctly. If there wasn't someone on site supervising the drilling, we can inspect the inside of the borehole to ensure that the casing is intact and the integrity of the casing is good. We can look at boreholes that were maybe drilled 30 or 40 years ago, and we just don't have the information on them anymore. Then we can go and take a look inside of those, as well as if, for instance, there's a production borehole where we remove the pump, and then when we reinstall it, it's not installing well, and there's an obstruction to the borehole, as is the case in the below pictures. This was a borehole that we camera logged where the casing was meant to have been installed to about 100 meters below surface. And in fact, when we put the camera in, it was only at 56 meters that the casing ended. We can see that there was large loose chunks of rock down the rest of the borehole, and we actually found casing again at 74 meters. So what this tells us is that during the drilling, there was obviously some difficulties with the casing installation all the way down, and at one point the casing must have been ripped apart, and clearly this is not something where you would want to install a long-term production pump to 80 meters or 90 meters or 100 meters, because you might lose it. There's a lot of sediment that can fall out of these loose chunks and fall into the pump and start causing issues in the pump, all sorts of problems. So if we don't have accurate drilling supervision, this can be a great way to check what the actual quality of the borehole is after the fact. Another thing that it can be used for is to check if there's an issue with the borehole in production after years of use. And this comes back to what I was talking about with precipitated metals. In this case, this is iron biofouling. We have a Johnson wedge wire screen on the inside of the borehole. At the top left, we can see the screen before there was any biofouling. After a couple of months of use, we have the image in the middle. The iron in the water got oxygenated, precipitated, and then we got iron biofouling on top of that, causing a clogging of these slots and a decrease in the efficiency of the borehole. So this is our camera that we use. We can get inside pump rooms and stuff like that because it's quite small. It's quite rugged. We can go out into the field with it, take a look down boreholes, get that information that we need to make sure that at the end of the day, we know what we're dealing with on the inside of the borehole. So in summary, we have national standards for the yield and the quality testing of boreholes. And it's important that we stick to these if we want to license these boreholes, because these standards protect us from over-abstracting the aquifer and causing impacts on surrounding groundwater users. This also allows us to make clear recommendations on what size pumps should be used for the boreholes, what depths these should be installed to, and how we expect the boreholes to perform in the future. In terms of quality, we need to be able to check that if the water is intended for drinking or irrigation, that the chemistry of the water matches that use. And we can also get a little bit of information on how the aquifer is producing that type of quality water and what type of geological conditions we're expecting that aquifer to be in. Lastly, if there's a lot of uncertainty, we can do a camera logging investigation, and that can add a lot of detail into what we understand about the borehole. Once we have all of this information, then we are at a stage when we can go to the Department of Water and Sanitation and say, okay, we know how much water we can get from this borehole. We'd like to apply for a license application. And for that, I'm going to hand over to Christel. Thank you very much.
Thank you, Kees. Hi, everybody. My name is Christel van Staden. I will quickly discuss what the legislative requirements are for when you abstract groundwater. Right, let me just share my screen. Okay, so I want to start with the National Water Act. This is where the basis is for legislation and why it also helps us govern and decide how we need to register our water. The main aim of this act is to protect, use, develop, conserve, manage, and control within accordance of certain factors our resources, and our groundwater resource is one of them. And I think in the past years we've noticed that it's quite a valuable resource and we really do need to protect it. So groundwater belongs to everybody. It doesn't belong to one person just because it flows underneath your property. It belongs to everybody, and the Department of Water and Sanitation is responsible to make sure that this resource is managed correctly, and therefore they are what we call the custodian of groundwater. In Chapter 4 of the National Water Act, it deals with what we call water uses. So you can use water in several ways. You can take water, you can store water, you can transfer water, and you can even use water for recreational purposes. And depending on the volume you use, it will dictate whether you need to license it or not. So as hydrogeologists, we mainly take water from our groundwater resource through boreholes, pits, or well points, and therefore I'm mainly just going to discuss Section 21A, taking water from a resource, which is in this case groundwater. So the law allows us 4 ways how we can use groundwater legally. The first use is what we call Schedule 1 use. This is reasonable domestic use within a person's house. It's for small gardening, for non-commercial purposes, for watering of animals within the grazing capacity of the land, which means this does not include feeding lots. You do not need any permission or registration for Schedule 1 use. The second use that permits you to use groundwater legally is what we call an ELU. An ELU is groundwater that was lawfully exercised in the 2 years prior to when the National Water Act was put in place in 1998. It's important to remember your ELU must be registered with the Department of Water and Sanitation. The third method of how you can use groundwater legally is what we call a general authorization. This is for small-scale abstraction. You can use a GA for commercial purposes. The volume is dictated by your property size and also the quaternary catchment you fall in. And a GA does have a maximum limit of 40,000 cubes per annum. If you want to abstract on large scale and the volume you want to abstract is over the GA limit for your property, you will need to apply for a water use license. This is a much longer and detailed process than a GA, A water use license is applied through the Department of Water and Sanitation. It's reviewed every 5 years, and it's issued for a maximum of 20 years and to a maximum of 40 years. We mainly, however, only see 20-year licenses. It's also important to remember a license comes with a multiple of compliance conditions, which I will show you a bit later. So the whole country is managed through water management areas, and as you can see here, the country is divided in water management areas. And in South Africa, in Cape Town, you can see we fall in what we know as the Berg management area. Each water management area is then even further subdivided in what we call quaternary catchment. Now, for an example to calculate whether you can apply just for GA or WULA, if you, for example, your property falls within quaternary catchment G10A, the general authorization for that quaternary catchment is 400 cubes per hectare per annum. Therefore, if your property size is 17, if you multiply 17 by 400, you get 6,800, which means you can use 6,800 cubes per annum with a GA registration. Therefore, if you use less than that, you do not need to apply for a WULA. In this case, the farmer wanted to use 55,000 cubes per annum, and therefore he needed to apply for a water use license. I don't want to go in too much detail about the detailed process, but it's important to know that it's an online process. A GA process is a much smaller process and not so detailed. It usually involves a pre-application inquiry where you link your client, you put in details of the application, and you put in information about the equity and also a signed affidavit. At that point, you submit your application to the department, and they assign an assessor to your application. At that point, the assessor or you will contact each other and discuss the application. And if it's found that it is just a GA, the assessor will open phase 1, where several forms are filled in with a lot more detail about the water use, in this case, groundwater abstraction. And then also several documents like IDs, title deeds, business registrations are also submitted to the department. Then you submit your phase 1. It goes through some internal processes inside DWS, and finally your water use is captured on WARMS. WARMS is a database. It stands for Water Authorization and Registration Management Database, and all our water uses are captured there. It's a way in which the department uses to manage our groundwater resource. So this is just an example of a GA authorization certificate. It's a quite simple document. It states the water use, section 21A, taking water from a water resource. It's usually just 2 pages long, and the only condition is that you need to use the water within the volume that's stipulated on the certificate. Now, for a WULA process, as you can see, it's a lot more complex. The first 2 steps are quite similar. You have a pre-application inquiry, a phase 1 where you start submitting some documents, and then the big difference is for WULA, the department usually requires a site visit where an assessor goes out to site. They look at your borehole, they look at your farm or the situation, and they make sure that all the water uses are applied for and that the license can be taken further. Then after phase 2, phase 3 is usually open, and this is where several more forms are filled in, and also your specialist reports. For example, for groundwater abstraction, you'll have a geohydrological assessment. Therefore, you'll submit that in phase 3, and then also another report, which we call a section 27 motivational report. This report is for other motivations as to why your water use needs to be approved. It looks at things like what you're going to use the water for. Have you looked at other sources of water? What is the benefits, the economic benefits of approving this water use? It looks at several aspects. After phase 3, your water use license is submitted to the department, and then it goes through a very big internal process. Your specialist reports goes to internal specialists, and your reports gets reviewed. The whole license gets presented in front of a committee called WUAC. It stands for Water Use Authorization Assessment Advisory Committee. And if they are happy and approve the water use license, they will give it a go-ahead, where it will go then to regional finalization, head office in Pretoria, and then lastly, your water use will also be captured on WARMS. As an example, for a WULA, it's quite a lengthy document. It's usually 5 pages or more, and it has several compliance conditions. It also has, the compliance conditions are divided in appendices. So appendix 1 is usually your I want to call it your stock standard compliance conditions. It deals with property changes, and it also deals with internal auditing and external auditing of your license. Every license comes with these compliance conditions. And then further on, Appendix 2 deals with the specific water use compliance conditions. For example, in this case, for groundwater abstraction, it's always there. You have to monitor the quantity of groundwater that you use, and you also have to monitor the quality. And in some occasions like this one, you also get special conditions. For example, here, 14.2, it was required that 2 boreholes are used as monitoring boreholes to ensure that the surrounding area does not get impacted by the water use. So one of the main reasons you need to monitor is your legal requirements, but there are several more. And with that, I'm going to hand over to Dale, who will discuss monitoring and management of groundwater a bit further. Thank you.
Good afternoon, all. I know it's been a long session, but I ask for 10 more minutes of your time as we go into a very important topic of groundwater monitoring. As Christel said, my name is Dale Barrow. I'm a hydrogeologist. I've been with GEOS for the past 12 years. So we've spoken through the various aspects and components of the groundwater development project, from exploration to drilling, the scientific testing thereof, and even the legal compliance. Last but certainly not least is the importance of groundwater monitoring. And I hope that during this next 10 minutes, I can show you some of the real value that you can take out and obtain from your borehole by monitoring it. Let's start with the question, why do we monitor groundwater? And there are a variety of reasons. I've just put down a few here that came to mind. Maybe it's contamination related. Maybe there's a contaminant plume that you're monitoring or trying to assess how it's breaking down. Or maybe it relates to what Christel has been speaking to, legal obligation to monitor, or part of your water use license conditions. Potentially, there are also environmental reasons why one might undertake monitoring. To the right of the presentation here, we've got a stilling well in a river, where we're monitoring to see how the river is impacted by groundwater abstraction from the Table Mountain Group aquifer. That's another reason why we monitor. But really, in the 10 minutes that I've got with you, I want to demonstrate how groundwater monitoring can benefit you as the groundwater user. And it really goes around optimizing your abstraction. By that, I mean making the incremental changes to your abstraction, the volume that you're pumping, to ensure that firstly, your usage is sustainable, that your bore is going to continue to supply you in the years to come. But secondly, that you're using it to its optimal capacity. And then I've also added the point there, assessment of aquifer health. What is the impact of your abstraction on their environment, on the aquifer? What is the impact of the valley's abstraction on the aquifer? We know that groundwater is geologically controlled. It's a shared resource. How is the aquifer responding to different stresses? And groundwater monitoring can help us answer these questions. when we talk about monitoring, what do we mean? And that's a good question, because there's different quantities or parameters that we need to monitor. If I draw your attention to the hydrological cycle in the bottom left here, we've got 2 boreholes abstracting groundwater for agricultural irrigation. Often when we talk about monitoring, the assumption is that we're talking about volume, the volume that is pumped out. And yes, that's often the volume that's reported in terms of compliance, or potentially, I saw we had, I think, about 30% of our audience is from the agricultural sector. So maybe you're concerned about the volume that you're irrigating on your crops. So yes, it's important to monitor the volume we're pumping out of the ground. But as important, if not more, is the water level response within the aquifer and within your borehole. The water level within the borehole is related to the volume of water that is stored within the aquifer. And so by monitoring water level of the aquifer, of the borehole, we're able to assess aquifer depletion, aquifer recharge, how the aquifer is responding, how the borehole is responding to abstraction. In addition to that, Kes also touched on some of the water quality requirements. And yes, we also want to monitor that, because water quality can change. We've seen it impacted by pesticides and fertilizers. So, or potentially over abstraction can pull in poorer quality water and result in deterioration in water quality. The frequency of that monitoring is probably less frequent than your volume and your water levels, but at least on a biannual or an annual basis, it would be worth sampling and checking the quality of your groundwater source. So practically, how do we do this? Here is a good example of a production borehole. You'll observe the flow meter for the abstraction volume that we're pumping, the sampling tap for the biannual water quality check, and then importantly and often neglected is the observation pipe. Now this is a relatively simple installation. It's HDPE pipe, not pinched, and installed cable tied to your riser pipe down to your pump. And that is perforated HDPE pipe that gives you a window into your borehole. It is using this observation pipe that you're able to measure the water level within your borehole. And I'm going to demonstrate the importance and the value that you can take as a groundwater user by knowing where the water level is. Then when you go to your borehole, what will you need? As a minimum, you will need a dip meter. And this is quite a nice fancy one in red here. You get much simpler, cruder designs. What you want to do is to be able to, at any point in time, go to your supply source and measure the water level. If your borehole stops pumping for some other reason, if you can't measure the water level, you don't know if the water level has dropped to pump inlet or if it's it's the electricity that's gone off. You need to be able to measure the water level at your borehole. We've spoken about flow meter, monitoring the volume. Another nice to have, and critical in some cases, is a water level logger, water level pressure transducer. What this does is this sits in your observation pipe or in your borehole, and it measures water level at a programmed frequency. So Solinst is a Canadian product that we commonly use in South Africa. We would install this and program it to measure water level measurements every half hour or every hour. And that data can then be assessed, and we get high resolution data in terms of the frequency of the readings to assess how the water level is changing in the borehole. And I'll demonstrate to you some of the conclusions that we can draw from those. It's probably worth just raising at this point that the frequency with which we do this monitoring will depend on the importance of your borehole or your groundwater source. For some groundwater users, it is critical. It is critical to their business, and they need to know real time where the water levels are sitting in their boreholes. And if I draw your attention to the top right corner here, this is water level data from 2 boreholes that is available on any internet-enabled device. What we do is we couple up the Solinst level logger to telemetry system, and that enables you to, from your house, from your office, from your phone, see where the water levels are in your borehole. And if you know the critical water level, which is what Kes was speaking to, you can have the warnings pre-programmed so that you can pick up when your water level in your borehole has dropped too significantly. For some applications, this is required. For others, where the data doesn't need to be seen real time, we do monthly or as a minimum quarterly monitoring, where we go to the field, we retrieve the data off the logger, and we assess how the water levels have fluctuated over the last month or the last quarter. And the graph in the bottom right is an example of the typical graph that we would draw. I'm going to show you a couple of examples. So I just want to quickly unpack what this graph is reflecting here. On the x-axis, we've got time series data. We've got about a year of data from this borehole. On the vertical axis, we've got water level drawdown, meters below ground level, and that's indicated by this blue line. When we go to the field, we take a manual reading that's represented by these red stars, diamonds. And what you can see here is the water levels fairly stable. And when the borehole switches on, the water level draws down. And when the pump switches off, we see its recovery. Here's a period of longer abstraction. We can see the drawdown during that period, and we can see the recovery. So that's the water level data we're looking at. Also on the vertical axis, we've got temperature. In this case, the temperature fluctuations are all within 1 degree, nothing substantial, but we do see that there's some variation when pumping occurs. Remember, we installed the logger just above the pump. So if there's any increase in heat in the pump, which we typically see if the pump's under strain or if there's going to be a pump burnout, we would get a fairly big spike in the temperature, and that would be a warning to us that there's something that needs to be attended to in terms of the pump. The pump is taking strain. But in this case, just minor fluctuations associated with the abstraction from this borehole. So what I want to now do is just show you a couple of examples of where this monitoring data provided meaningful information to the groundwater user that allowed them to make informed management decisions. So in this case, this was in towards the middle of 2018. It was the peak of the drought. The day zero scenario was still real. And this groundwater user raised concern. They actually contacted us asking us to drill them a second borehole. They were very dependent on their single borehole, and they realized that if this borehole gave in, their restaurant and the farm would be in a serious predicament. And as often occurs, I couldn't even measure a water level at the borehole. So my first recommendation to them was, let's put a water level logger in. Let's see how your current abstraction is impacting on the aquifer. How are your water levels performing? And from 1 week of data, we got fairly good data where we see the rest periods, we see them switch on their borehole and the drawdown within the borehole, and we see the recovery within the borehole, and followed by another period of abstraction and recovery. By assessing this data, we could tell them two things. Firstly, they can rest easy. This borehole usage is very sustainable and is not going to fail in any time soon. And secondly, they can double their abstraction from this borehole before they need to consider drilling an additional supply borehole. So real information that benefited this user and saved them the expense of having to drill a second borehole. That was 1 week of borehole data. In this case, this client, we've got over 10 years of data now. And what you see is the summer peak abstraction periods with the drawdown, and then the recovery periods. Again, we're going out monthly, so the red diamonds are frequent. The blue line are hourly data, so very high resolution. I'm sort of giving you a big overview of the 10 years of data. And again, the question during the drought, they knew exactly where their water levels were. They could make incremental changes to their abstraction to ensure that they were going to have continuity of supply from their borehole through the peak of the drought and through the peak of their demand. You will notice that when we started with monitoring, the water levels were initially drawn down to pump inlet. There were issues with pumps burning out. And apart from those first 2 years, you can see how the abstraction is sustainable. And this is really just a great example of informed management of the supply source. Here's another example where year on year, we see the water level within this borehole being drawn down deeper and closer to that first fracture depth. And this is potentially an example of the abstraction increasing year on year. And this is the sort of information that the groundwater user would need to use to calibrate their abstraction and ensure that they don't drop their water level any further in the year to come. There's other interesting aspects that one can pull from groundwater monitoring data. And in this graphic, we've got two boreholes located a few hundred meters apart. But when we plot their water levels, we see that they are almost identical. And these boreholes are both located in the same aquifer, and you can see it from their signature. And where you've got multiple boreholes that are abstracting from the same aquifer, as the graph that Kes showed, you can then start to see to what degree these boreholes impact on each other, which is again critical to the management of your borehole or your boreholes. The monitoring data helps you make informed decisions on a daily basis if you're watching it at that resolution, incremental changes to your abstraction, but it also gives you a big picture of how your aquifer is responding to stresses. And one of the stresses that we're all too aware of is that of drought. And this is in the central Karoo, where in 2010 we were in a very bad situation. You can see how the water levels were very low and how they came up nicely in the subsequent years. But for the last approximately 5 years, we've had below average rainfall indicated by the light blue columns. And actually in the current situation, we reach lower water levels than we did in 2010. So it's a serious situation in the central Karoo. But by watching the water level, we're able to assess the impact of drought. And we don't just want to watch our water levels along with rainfall, we also want to see how they respond to our abstraction. So in this case, we plot the abstraction from this borehole. We'll see that it only really kicked in when the drought started in the central Karoo, and how the water levels have then responded to the abstraction from this borehole during this drought period. Another stress, the opposite of drought, is when we get a high rainfall event, a recharge event. And I've included a picture here of a stilling well for a river. And typically in a river flow hydrograph, when you have a rainfall event, you get this immediate peak in the water level and then this gradual recession of that line. And interestingly, for this borehole, it has a very similar signature to a streamflow curve, where it responds immediately to your rainfall event. So you have a rainfall event, immediately a water level response, and then a gradual drop in that water level. And what that tells us is that this borehole is in the recharge zone. It's in the Table Mountain Group aquifer. And then another example, again, going back to the drought, which we've just been through. This was a borehole where the water level was being drawn down. Obviously very difficult for this groundwater user. It was an industrial use and trying to manage the water levels. But in May 2018, we had good rains again, and the river flowed, which is the first time it had flowed in a while. And immediately we saw this inflection in the water level data and the recovery thereof. And this is a fractured rock aquifer. So yeah, we're sitting at fractures about 40 meters, but obviously also relatively quickly recharged, especially by the alluvial channel. And this is the sort of data that you need as a borehole operator if you're using groundwater, to be able to know when you can start using your borehole at capacity again, and how to incrementally phase that back in. So to summarize, why should us groundwater users monitor our use? Ultimately, it's about making sure that our supply is available for the season to get us to the next rainfall period, but also for the years to come. I've mentioned briefly infrastructure management. We can sort of pick up if a pump's going to burn out, we can avoid drawing the water level down to the pump. But Kes also touched on the issue of iron biofouling. And often that is aggravated by over abstraction and by dropping your water levels too excessively. So we can make meaningful contributions by just managing our abstraction in terms of reducing our expenditure on infrastructure. And then really the big ones are optimization of use. enabling you to make those incremental changes that ensure your use is sustainable and also ensure that you're meeting your demand, the volumes you need to get from your borehole. And ultimately, it's about having the data on hand to be able to make informed decisions. So it's about informed management. I'm passionate about it, and I'd be glad to take questions on it, but I think at this point, you've heard a lot, and I'm going to hand back to Christel to manage the questions.
Thank you very much, Dale, and thank you for everybody participating. We don't have a lot of time left, 10 minutes, so I'm gonna jump right into the questions. I'm gonna start with Mark Maynard, and you, Kes, can I please ask you to answer this? He's asking, do you need an observation borehole during yield testing?
Thank you, Christel, and thanks, Mark. So an observation borehole, it depends on the purpose of the yield testing. So if the yield testing's purpose is purely for the sustainable yield of the borehole, then no, we don't require an observation borehole to monitor during the test pumping. However, if we're looking at requiring accurate aquifer parameters, then we do need the observation borehole, and we might need those aquifer parameters for modeling, for numerical modeling of the aquifer. We might need them for better predictions on whether we can impact surrounding boreholes or not. But at the end of the day, if we're just talking about the sustainable yield of a single borehole without impacting on other surrounding boreholes, then we don't need that observation borehole during the pumping test, although it is always helpful to have that data.
Great.
Back to you, Christel.
Thank you, Kes. Neville, one question for you. Apologies, here it is. Where do the theoretic current measurement method fits in, or which part do this method help to identify borehole site? Yes, can you please answer that question?
Yes, thanks Maggie for that question. So the PQWT method is still relatively new in the groundwater fraternity. It still has to be proven. There's questions behind how it collects the data and what the data actually means. We have tested it, and we had small issues with battery life and when working in temperatures above 35 degrees. And often that's the issue. If you've got the best equipment, it's got to be reliable in tough areas, remote areas where we often find ourselves. It is a very interesting method, and it looks like it has great potential. So ideally, we'd run a test run on it and then run it close to, let's say, the three more major geophysical methods, and just basically prove if it works or not. Hopefully get budget to drill after that. Yeah, I hope that answers your question.
Great. Thank you very much, Neville. I'd like to ask you another question, to answer another question, Neville. Somebody asked, in terms of drilling, what determines the depth at which you stop drilling once you have a desired blow yield?
Yeah, Zulani, thanks for that question. Great question. So if you've met your desired blow yield, you must bear in mind that that's not necessarily what you're going to get. Often it's lower than that once you've tested it. If there's budget available, and if you're still in that good geology, there's no reason to stop, carry on. Possibly that'll increase the blow yield. If it's, for example, way above what you need, we generally go 10 meters beyond that, just to form a bit of a sump. And what that sump does is it just forms as a little capture zone for any sediment or what have you that comes out of the fracture whilst they're developing the borehole. And also, you've got other cases where you drill just past that fracture and you suddenly come into a rock that gives you poor quality water. Then you should even stop before drilling 10 meters past it. So it's quite the answer to that is quite dependent on the situation.
Great. Thank you very much, Neville. Kes, I'd like to put this one to you. Can one use the radius of influence to justify the number of groundwater or surface water interactions in case the borehole is located close to perennial river?
Thanks. That's a good question, and often quite a topical question from the Department of Water and Sanitation when it comes to licensing the use from a borehole. And it's always a topic that has to be addressed when there is surface water bodies that can be impacted on from a borehole. Specifically using the radius of influence to definitively say that either yes or no is not what I would recommend. It can give us an indication of whether we expect that to be a potential occurrence or not, but I would rather do something more definitive, like looking at the derivative plot of the drawdown data during the pump testing. That is a great way to look at surface water groundwater interaction. Alternatively, chemistry sampling of the groundwater compared to the surface water is a good way to go about it. And I would absolutely go for an isotope study in that case as well. And then with those three methods together, as well as using the radius of influence, that would be a much more definitive way to say we expect these two to impact each other and might need to restrain use a little bit so that there isn't that impact on a surface water body, or to say actually we can quite clearly see these are two completely different waters or water types or water bodies, and we don't expect any interference between them and use can go ahead as planned. So that's the approach that I would rather take, and the radius of influence would be a small part of data that we could add to a collective study to determine that question. Yeah, thanks.
Thank you, Kes. Dale, the next question is for you, please. Do you guys do any monitoring for seawater intrusion? How do you go about it?
So typically, saline intrusion is obviously a huge concern in your coastal aquifers, and it's not something you would want to address at your production borehole level. So the monitoring that I presented is even your production borehole, you can extract monitoring data of value to you. But for where you've got a risk of saline intrusion, you would almost certainly need designated monitoring boreholes, strategically located, and you would need to do some form of modeling, probably numerical modeling if it's large-scale abstraction, to ensure that your abstraction isn't going to pull in saline water, because that can have far-reaching consequences. So I know how that's happening with the Cape Flats aquifer is there's a lot of research that's going into the project prior to the commissioning of your abstraction wells, and even including managed aquifer recharge, so putting fresh water in at strategic locations to ensure that there isn't saline intrusion, and obviously there'll be the monitoring to supplement that, to monitor against saline intrusion. That's somewhat slightly different to the sort of monitoring your production borehole, which I've touched on today, but it's certainly a topic that we could spend 2 hours on. So I've sort of I've said a lot of general things, but I think there's a lot more detail that one could go into on that topic.
Thank you, Dale. Before I ask the next question, we're running quite close to 5 o'clock, and I'd like to run one last poll with regards to what topics you guys would like us to cover next. I'm going to continue with the questions, and as you guys answer the poll that we'll just run, and I'll share the results in 2 minutes. So next question, Neville, this one is also for you. Is there a reason that led you to drill to a second fracture aquifer, sandstone in the Karoo?
Thanks for that one, also very good. So the basics of the dolerite, once it intrudes your sedimentary layers, it's a very hot magma, and that heat causes your surrounding layers to expand, and when it cools down, it causes contraction in those surrounding sedimentary layers. So you get like a damage zone around the dike, and essentially what that does is it links your sedimentary zones, and that's basically why guys doing all the fracking try to avoid dolerite dikes. But from a groundwater aspect, if you drill into a deeper sandstone bed that's fractured and it's next to this dolerite dike, the chances are your water yield is going to be higher, because it's essentially being fed from the top, from your alluvium, from your surface, and it going down through each layer. So yeah, if you can plan it that you intersect a sandstone for good quality at a deeper depth than a shallow sandstone, chances are your yields are going to be higher. Thank you.
Thank you, Neville. Neville, I'm going to throw another one at you if you don't mind. During drilling, is there a definite way to identify that you've intersected another deeper water strike?
Yes, there is. So the best practice is once you're drilling a hole and you're on site supervising it, and there's a water strike, try and develop that hole for a couple of minutes and take an airlift yield. And then if you continue, the hole will improve over time. The blow yield generally improves. But if you hit another water strike, it'll be a noticeable increase in yield. And then you take another measurement. And in the ideal world, you're going to have an EC meter and you're going to check the quality of that first water strike. Once you hit that second one, you can check the quality of the second water strike. It'll now be a cumulative quality, but it should change if they're different aquifers. Thanks.
Great. Thank you very much. I'm going to end the poll now and ask Julian to end our meeting. I'm sure we can do some more questions afterwards, but for those that are leaving, I think we should try and end the meeting now. Thank you, Julian. Over to you.
Thank you very much, Christel. Interesting. Thank you very much, Christel. Thank you to the fantastic speakers this afternoon. It was greatly appreciated. And thanks to everybody for your time and for being here this afternoon. And if you have further queries, please contact Christel van Staden, c.van.staden@gls.co.za. You've been in contact with her already. So if you would like the presentation or like the recordings, please do contact her. But that's it from my side and our team. And I want to sign off and thank you all very much. Okay, cheers.